Let's talk about ED301, which is showing the Windows stack pointer, same thing I talked about in the lecture. So first you have to install Visual Studio, which you'll find, the instructions here if you don't already have it. I think you've already got it from earlier projects. Visual Studio C++ Build Tools from Microsoft, which is Microsoft's free C++ compiler, which is essentially the equivalent of GCC. So we're going to make a program here. So you go into Start and then scroll down to the Visual Studio section, V, and open Developer Command Prompt for VS 2019. This is going to be 64-bit code, the default, which is fine. And so you make a directory to put your stuff in. I'll just make mine demo and go into there. Make dir C demo CD demo. All right, and now I can make source code with Notepad, which is pwd.cpp, because this stuff is in C++, which is a lot like C with a few small differences that we don't really care about. All right, so this is the C++ header that gives you the standard I/O libraries. Here's the main routine that just calls a test PW subroutine. And there's the test PW subroutine, which in fact has a buffer overflow vulnerability, but it doesn't really matter for what we're doing here. We're not going to be exploiting that right now. So I save that, and now I'm just going to compile that a couple of different ways. I'll copy it to a second version of it called pwdn. All right, and now I compile it with this EHSC, which I think is not actually necessary, but I was in the tutorial I was following when I started doing this. So this will compile it normally, and it'll create pwd.exe, and then I'm going to make one with the gs- switch, which is going to turn off the stack protections, and I'm going to call that pwdn for no stack protection. There we are. And so if I do a directory, you'll see that pwd.exe is 204.288, but pwdn is 203.264, about a kilobyte smaller. So with no stack protection, it's of course smaller. It has somewhat less code in it. So if we look at it in IDA, we've got IDA here. Disassemble a new file and go to C demo. All right, let's look at the one with the defense, pwd, and I'll just accept the default analysis. And it's still loading as the colored bar changes. All right. And the space bar should take me to graph view. Oh, maybe I got to hit this. There we go. So now I can see these little blocks of code. And as usual, the only thing you see when you typically look at something is just the loader. Nothing very nice. So I usually look for the strings, is the easy way to find the good stuff. View. I said view. Open subviews. Yes, it's view, open subviews. It's sort of slow and laggy. Okay, now I can go to strings. And here's the strings showing things like enter password and fail, which is too small, but anyway, it's not worth struggling here. That'll take us to where the password is stored, enter password. Let me just take a minute and see if I can make the font bigger. This is annoying. A font, oh, maybe I can. Options, font. Let's just try making it Lucida and something bigger like 14. Okay. Oh, good. So now it's showing, all right, so this is where the data strings are stored. This is the R data section, and here's where the password is stored, and here's fail and you win. And this is the cross-reference leading to the code that uses that value. So you double-click that, and that takes you to the routine that takes the password, and this is where the buffer overflow is. And here you see the security cookie. So the prologue does include loading the security cookie, and when you leave, it should be checking for that. So if we go down here, when it's done, yep, here it is. Before it returns, it calls the security check cookie routine. So that's the security cookie in all its glory. And if we look at the version of this program, let me just see if there's anything else I want to do with this one. I don't think so. There's a flag to look for as well. But anyway, let's look at the one without the defense. That's file open. Here we are. Don't save the database from the old one because I haven't done any analysis that I care about. And open pwdn. The default analysis again is good in IDAPRO. And it's still working. This window at the bottom will show me when it's done, and also that bar stops changing color too. It'll be done. And I think it's still working, which is part of why I didn't get a good response before. But I want to do View, Open Subviews, Strings. And then here's Enter Password. That would be good. I wonder if I can get these fonts to change too. It doesn't work. I'm not going to do any more of this. Just go to this one there. This one's big. There's the Enter Password. Double click that to see the code that uses it. Hey. That's rude. Oh, I see. It's here. It's just not in the right view. Hit space to take it back. All right, now you see. Here it enters the password where there might be a buffer overflow. And here is when it's done calculating to see if you had the right password. And it just returns. And you see it does not check the cookie before it returns. And it does not set a cookie when it enters. So this is the old-fashioned code compiled with no defense against buffer overflows. So that's really all there is in this one. You get to see that. And let's take a look at the next one, 302. All right. You get a developer command prompt. We take the same program, compile it normally, and then we're going to compile it without ASLR. So I'm going to close this. Don't need to save the old database. I can use the same directory. If I do directory here, I have the pwd.cpp, and the normally compiled one is here, pwd.exe. And so if I want to make one without address space layout randomization, I copy it to, oh, I see. Oh, I need to do a different program, pardon me. I need to make one that's going to show me the stack pointer, so let's do that. Notepad, esp.cpp. This is a C program that will let me see the location of some data in memory. So here's the code for this one. Okay, so what it's going to do, you can include assembly code in C this way. So I define a local a data here, which is going to be on the stack inside this routine, and then I just move the location of that to ESP with this assembly language command. And now I can just print out ESP. All right. I print out that data here. All right. So what I did was I defined, let me try this again. I said that wrong. I defined a data variable. Now I take the stack pointer and move it into there. So I have a copy of it. And now I print my copy of the stack pointer. This is how I was able to show an address on the stack. And then I just have press enter to continue so it won't close right away so I can see it. That's all this one does. But it lets you see an address that's on the stack. And that gives you information about the memory locations being used by your program. So I want to save that. And now I want to compile it the same old way with ehsc and esp.cpp. All right. And now if I run that, there it is. So there's an address on the stack. And if I run it again, There it is. And notice it keeps changing. 12F, 93F, and so on. So this is address space layout randomization, which is on by default in Windows, and in fact not easy to turn off. I'm not sure you can turn it off at all in modern versions of Windows. But what you can do is you can compile your program with that defense turned off. So you can take esp.cpp and make esp2, and then do the compile again for esp2, and here you put in first you cl it /c to compile it but not link it. So that will compile it and create object code but not executable code. It's the first half of making it executable. The second step is to link it, and here you link it with the dynamic base no switch. Dynamic there. You link the object code without letting it randomize. And now if I run that one, every time I run it, the address is the same. So we did this, by the way, in Linux with the, there's a tool to strip away the randomization called set dill characteristics. So you can do it, as for Windows malware, you can do it. Anyway, this way, so now I've made a compiled version that does not have randomization. So now we're going to make pwd3. Let me put this in here, Notepad. All right. Again, this one is going to have the same old thing with a simple buffer overflow address, and it's also going to print out the stack location, as we've seen before. All right, so we'll compile this thing without address space layout randomization. So save it and close it. And let's do the CL here, pwd3. All right, that will make object code. Now we link it with a dynamic base. Turned off. So this will make a program that does not have address space layout randomization. So let's run it. pwd3. I'll give it a password of 1. If I run it again, password of 1. This number is always the same. It's not randomized. All right. Now we can take a look at immunity. All right. And Mona, which we've already got installed from previous projects. And we can debug this thing in immunity. All right. File open. And it's C demo pwd3. All right. We can run this thing. That will open a box here. It will ask us for a password. And so it's A through H, A. All right, A through H is 32 letters. And run, and now it's going to hit an exception. And I expected it to give me overflow. Was unable to process the exception. That makes me think, all right. That's disturbing. There should have been an overflow. This was pwd3. This makes me think the data execution prevention is turned on, which it shouldn't be. I checked it already on this box. Let me see what the deal is. Let's get out of this. and take a look and make sure I'm doing things right. Oops, I had to be in the, no, I don't really have to be. All right, let's go here to demo. It was PWD3, right? Yep, so 1, 2. Well, that crashes. Yes. All right, let me just check. I'm pretty sure I've already done this, but let's make sure that I don't have data execution prevention turned on here. That is, oh, not there. It's in PC properties. Advanced system settings. And system advanced performance settings. Here we are. Data execution prevention. So this is turn on DEP for essential Windows programs and services only. That is the lower level of protection. So, all right, I may be in trouble here. I expected to see it overflow. And, well, maybe I'm not going to get any further than this tonight if I'm just getting this much trouble. Unless any of you see what I've done wrong, I appear to have made a mistake of some sort. Let's open PWD3 in the demo. Now, I checked these about a month ago. I might try running the other one that I made in the other directory. Let's see if that does. Anyway, so the point is here, I run it, and then I put in 32 letters. So let's try one more time, and then I'm going to try the other one and see if I can figure out what the problem is. So it's 1, C, 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 C. Yep, debug program was unable to process exception. Okay, now if it's going to give me grief like that, I'm going to just try running the other one that I prepared a month ago. It's just in a different directory here, and we'll see if that one works. File, open. That's just in the C127 directory. All right. And PWD3 is here. What if I'm doing the wrong problem? The wrong program, that would do it. It is PWD3, okay. Now let's run this one. Okay, and give it that password. Not listening to me somehow. Okay, nope, still not listening to me. Breakpoint, oh. It's got a breakpoint? Oh, there's a breakpoint in here. Okay, let's clear that with F2. Okay, it remembered the breakpoint from when I analyzed it before. Now it's running. Okay, good. So I put in A, B, 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 C, 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 D. Yep, and now I get access violation when executing 48, 48, 48, 48. So this one's working. I don't know what was wrong with the last one I did. Let's take a quick look back and see if I can spot my mistake. That's it, PW3. Just compile that program. All right, well, I'll carry on with this one. I must have made some mistake in the source code, I guess. Pasted it in. Anyway, the point is now you can execute the buffer overflow right here in the debugger, which is what we're going to do. All right. So now we're going to find, okay, right here in the lower pane of immunity, we're going to see the stack at the time of the crash. And the second word here is the return pointer. So we right-click that and follow in the disassembler. And we're up here. And this is the code that starts at 401,000 up here. All right, so now you can read the assembly code here. If you go down, remember, you always see helpful information on the right-hand side. And so here is the string ESP equals that we put in where it's going to print out the stack pointer. Here's where it enters the password, and so on. Okay. Now the push instruction here, E5, that puts a pointer onto the stack. And the call here is what prints that message out to the user. And the next call here is where it reads data in from the user. And you can see here, it's not as obvious, but anyway, this is the call that reads data from the user. This one here. So we put a breakpoint there, and you see there already is one there because I've done it here before. F2 takes it away, F2 puts it back. All right. So we put a breakpoint there, and we set another breakpoint on the instruction after the call, and now we can watch the buffer overflow in the debugger. All right, so now we go down to find the UN message. And what we're going to do is play the UN message. So here's fail, and here's UN. And so it's 401,270. All right. And so if we go to this location, it will push the UN message on the stack and then call something to print it out to the user. So if we can put that address on the stack, 401,270, we can get to the UN message. What we're doing here in Windows and the debugger is the same thing we did in Linux in GDB. All right, so we debug, restart. Hits the breakpoint and stops. So over here you find ESP and EBP. It's FF74 to FF80, which is what you see here. Here are the values. The word after EBP, 7F4. All right, it was 34 here, right. So EBP is FF74. It's FF80. So here's EBP. This is the return pointer here. So remember, when we did in Linux, we would highlight it from ESP to EBP. So you highlight from 74 down through 80. That's the stack frame. Here's the return pointer. I'm just feeling a little, we didn't run it yet. All right, pardon me. That's why I'm not liking what I see in the stack. Let me run it. There we go. Now we're here. Now it's asking for the password. Now I like it better. ESP and EBP, 00 to 20. So this is the stack frame. There we go. And here's the return. It should be in PWD. This is the return pointer that's going to go from this subroutine back to the main routine. That's what we want to overflow. So now we perform the overflow. We run to get past this breakpoint. Now it's ready to take the data, which is the same thing, A. All right. Now we are ready to go. And if the return pointer was after EBP, which is 20, it's right here, 48, 48, 48, 48. This is the value that's going to crash, so we need to modify that address and put in the target address. And you can do it here in the debugger with edit. And in here you can put in the address. The desired address is 70 12 40 00. That will point to the win message. So I say OK. And now I run it again. And now, in here I see you win. So this is the Windows version in the graphical debugger, showing you the same sort of thing we've done before. All right, and you can continue and write an exploit in Python to do the same thing, which is just printing out these the same exploit, and therefore that's what goes on with this one. All right, and I was going to do 303, but I'm thinking maybe I won't tonight. We'll talk about this one next time, I think, because I'm sort of stumbling around a bit. Like I never did figure out what was wrong with the code I created this time tonight, so I think I'll call it a night. That's 301 and 302.